My name is Dillon Kearns. I am an Elm trainer and coach, so if your company is looking for help transitioning to Elm, check out incrementalelm.com or come find me in chat. I'd love to hear from you. So today I'm going to be talking about types without borders. But before we talk about types without borders, let's talk about types or no types. So many of us have had this experience. We're writing this JavaScript code and we're excited to run our app and see what happens. JSON.parse string from server. And JSON is not defined. So of course we should have written it with all uppercase and then something interesting would have happened. But we didn't know that until runtime. And I mean, come on, we have to run our app to know things? We can do better than that, right? Well, the Elm Compiler is one tool that really helps us know a lot of things about our code. It's pretty smart. It knows things at compile time. It helps us make impossible states impossible. And overall, we get this sense that if our code compiles, it works. That's trademarked. And this is really what compels me to use Elm. I mean, I love that sense that I have that security, that if it compiles, I'm confident that it works. So let's talk about one of those experiences where we have that confidence that if it compiles, it works in Elm. So we're writing our nice little app. We've got it in a compiling state where we've got our custom message type that only has an increment message that can come into our app. So we're telling our update function what to do when an increment event occurs, and everything's good. We decide to handle a new message type, decrement, and the Elm compiler gives us this friendly, helpful error message. This case does not have branches for all possibilities. So great, thanks Elm compiler. We handle that new message, tell it what to do, and again, if it compiles, it works. We've got a lot of confidence that when we check it out in the browser, everything's going to be looking good. So that's what we want. We've got this certainty, we're in our happy place. Now let's compare that to another experience that if you've spent some time in Elm, you've probably encountered doing JSON decoding. So you're hitting a JSON API. Now there's some pretty cool things we can do doing JSON decoding in Elm. For example, here we've got a custom type character, which can be either a human or a droid. The humans and droids have different attributes. They both have names. Humans have home planets, and droids have primary functions. And we can have a decoder that decodes into that custom type. That's pretty neat. We decode the field type, and we expect that to be a string. And then based on that type, we're going to check if it's human, then we're going to run our human decoder. And if it's droid, we're going to proceed with our droid decoder. And if it's neither of those, something went wrong, we had an incorrect assumption, and it should fail with this message. And then here are the details of the human decoder and the droid decoder. You know, so it's this can trip people up when they're starting out with Elm. It can be a little bit tedious, but actually it's a really cool feature of Elm. But the thing that that's concerning about it is that we don't have a lot of guarantees. So our code compiles, so it works, right? Well, we run it, and we get this error. Bad payload, expecting an object with a field name, but instead got. So one of our assumptions in our JSON decoder was incorrect. So I thought we were past this, right, with Elm, where if it compiles, it works, right? So a little bit about our assumptions here. So compare this to the experience of dealing with JSON in JavaScript. So we've got our greet function, and we're passing in some JSON data. We're pulling the name attribute off of that JSON data, and we're greeted with hello object object. So in Elm, we would never get this because before it even calls our greet function, we would see that we had an incorrect assumption when we decoded it. And instead of getting a successful response back, we would get an error in our decoder. So that's quite cool. We have these explicit assumptions, results, and we know at the gate, as soon as we get our JSON data, that something went wrong. That's a wonderful feature of Elm. But wouldn't it be much nicer if we had no assumptions at all, like we do with our JSON decoders? So when can I know things in an application? Well, you can know things at compile time. You can know things at startup or build time, at runtime, or upon deeply running your application. So for example, when we looked at adding a decrement message, the compiler was able to tell us, hey, you haven't handled everything. OK, now you've handled everything. We knew that at compile time. At startup time, you'll know things, for example, whether your flags check out, whether they're the right type, and you're passing them incorrectly. We saw at runtime we had that bad payload error. So we knew that when we ran our application. And then with our JavaScript greet function, we didn't know when the JSON response came back that something went wrong, but we knew because it was lazily checking those assumptions. So that's upon deep running. So let's talk a little bit about uncertainty. So there are two types of uncertainty that I'm going to talk about here. One is unavoidable uncertainty, and the other is avoidable uncertainty. So what is unavoidable uncertainty? Well, so this is from the HTTP error type in Elm. So you can either have a bad status, a timeout, or a network error. And as far as I know, there's no way to guarantee that a user is connected to Wi-Fi. So it's really nice to know if there's a network error. So I can have some compiler support to say, hey, you forgot to tell me what you want to do if there's a network error. How do you want to handle that? That's awesome. So we love having unavoidable uncertainty represented. That's a wonderful feature. Now, avoidable certainty. So you could argue that bad URL is actually some uncertainty that could be avoided potentially. You could potentially come up with some domain-specific language where you could guarantee any URL that you build up is guaranteed to be valid according to the URL specification. So maybe we could make this impossible, but that's not what this talk is about. This talk is about types without borders, and this is kind of just types. So I'm going to skip over that one for now. What I'm really interested to talk about is this bad payload error that we saw earlier when we ran our JSON decoder. And so, again, we had these assumptions about the response that we're getting back from our server. So in a way, we had two sources of truth. What we're actually getting back from the server and what our JSON decoder expects to get back from the server. So this is kind of what it feels like to me when I'm working with an Elm application that has some avoidable uncertainty, like decoding JSON. It compiles, so I think it works, but I have a little bit of uncertainty because there are some things there that I have to kind of run to know whether those assumptions are correct, like my JSON decoders. So I'm pretty sure my code works. I make a change, I run it, and I see if there are any errors, like our bad payload runtime error that we got. Now, these aren't exceptions, which is really nice. They're errors. We're explicitly representing that uncertainty, but still, I have to run it to see if it's there. So if we get any errors, like JSON decode errors, we fix them. We run it again until there are no more errors. And then finally, we cross our fingers, and we hope that our app is working. We're pretty sure it is. So that's not really what we signed up for working with Elm. We want to operate in this world with certainty, where if it compiles, it works. So we've got this code. We're very confident that it works. We make a change, like adding our new decrement message example earlier. We compile it. It says, you haven't handled all these cases. We fixed the compiler errors, and once we've gone through that loop and fixed all the compiler errors, we're happy. We're very confident that our code is working, because we're operating with this single source of truth. So we've got this strong sense of confidence. So let's talk a little bit more about that interaction between Elm and a JSON API. So we're operating within the context of Elm, and we're happy. We've got these nice guarantees. We've got this certainty and confidence. And then, within the context of a JSON API, if that JSON API returns an integer to me one time and then a string the next time, is there a contract somewhere that it's violating? I mean, not really. It's kind of just, there's no explicit contract that says this is what is valid for this server to return. In fact, it's not uncommon that you'll have a JSON server return back HTML sometimes, and then your code is just completely confused. So I can't really have a lot of certainty when I'm operating just with vanilla JSON APIs. And so, of course, that area between Elm and JSON, I can't really have a lot of certainty. What can I send out to that JSON server? What can I expect to get back? I have to make a lot of assumptions. Let's compare that with GraphQL. So GraphQL is a pretty neat framework for building up APIs on the server side. So it gives some really strong guarantees. It helps enforce contracts. So for example, if you have a query that requires an argument of a date to be sent through, you can have the framework itself check that the date is able to be parsed correctly. And if it's not, the framework takes care of sending a nice, friendly message to the users. And if it is, it will proceed through and execute the code to make the request. So it enforces these contracts for you. So you get some pretty cool guarantees coming from the fact that the framework is enforcing them for you based on the schema that you specify to describe the types in your API. And it's got a pretty robust type system. So for example, in GraphQL, you can represent enums, like this sort order, which is either ascending or descending. That's pretty neat. You can represent objects. So this object is a character, and it has a name. You'll notice after the type there, string, it has an exclamation point. And that just means that the name cannot be null. So that's pretty cool. We can represent nullability in our GraphQL schema. And you'll also notice that home planet does not have an exclamation point. So that means that home planet could be null. You'll also notice that the friends type here is returning back a list of characters. So it can refer back to itself. So in that way, you can kind of represent these relationships. So rather than doing several requests like you do for a REST API, you can do in one request grabbing several different things and traversing these relationships. So that's the graph part of GraphQL. So this is, you can also represent arguments in a GraphQL API. So this is defining the top-level query. So a query in GraphQL is essentially like an endpoint in REST. So in this query character, it has an argument of ID. And you'll notice again that there's an exclamation point after the ID. That just means that's a required argument, not an optional one. OK, so you could kind of visually represent a GraphQL schema with something like this. And a query looks like this. So we're making a query, and we're getting all characters. And for each of those characters, we'd like to get that character's name, avatar URL, home planet, and that character's friends' names. OK, so GraphQL gives us some pretty cool guarantees and certainty within the context of our server API. But what about that space in between? We still don't have a lot of confidence there. So that's where this library I've built, Dillon, Kearns, Elm GraphQL, comes in. So this library essentially generates a hard-coded library for your particular GraphQL schema. And instead of you writing your JSON decoders and telling it, I expect this to be a string, I expect this to be an int, it treats JSON decode as an implementation detail that's taken care of for you. So it gives you some guarantees. For example, you're guaranteed to make a correct request to your GraphQL server. So if your query that you're making has a required argument, if you don't pass in that required argument, your Elm client code will not compile. It's well typed, so you know that if you're getting a character's name, it's going to be a string. If you're getting a character's home planet, it's going to be a maybe string. And it's guaranteed to decode correctly because the decoding is done for you in an auto-generated way. So you auto-generate this code using the Elm GraphQL command line interface. So if you're familiar with the JSON decode pipeline, it looks a lot like that. And if you're not familiar with JSON decode pipeline, it's just a light wrapper around the standard Elm JSON decode library. So here we've got a record type alias character info. And so that gives us this record constructor for character info. We begin the pipeline with the character info record constructor, and then we build up with all these decoders that are going to be funneled into that record. So Elm GraphQL looks very similar. You'll notice the main difference here is that we're not telling it this is a string, this is a nullable string, because those are low-level details with this library. This also defines not only the decoder, but the request we're going to make. OK, so let's do a demo. Okay. So this is the query we want to make. So we're doing a top-level query, and we're getting all characters, and for each character, we're getting these details. So now every time we do this for each, these brackets, that's called a selection set in GraphQL language. So, so we're going to do a query, and we're going to do a selection with, so we give the record constructor here, and we're going to get all characters, and we're going to pass in a character selection here. So I'm just going to make this constant here, character selection. This is the character selection that we want to build up. But for now, I'm just going to select the name in the character selection. So we build a character selection, and I'm going to use this character info record constructor for that type, and then we're going to pass in character.name. Okay, so it's grabbing data. I've got a little view helper here that if it's to do, it's not going to render the details. If it's done, then I can pass in some data. So I'm going to pass in the name there. And there we go, we've got some names. I'm going to grab the avatar URL now. And actually, you can see in this error message, it can be a little difficult to learn to read these pipeline error messages sometimes, but this is telling me that it expects the type to be a string. So avatar URL is a string. So now it's compiling. Let's pass it into the view helper here. And there we go. We've got some avatars. And then finally, let's grab the home planet. And you can actually see here that it knows that the home planet is going to decode into a maybe string. And actually, you can even see the documentation from that GraphQL field, which is pretty cool. So when it auto-generates this code, it grabs the documentation as well. So home planet is going to need to be a maybe string. And it's a maybe, so I'll just do maybe with default question mark. So there we go. Luke's from Tatooine. We don't know where Han Solo's from. So that's Dillon, Kearns, Elm, GraphQL. Now, one more note on this library. So let's say it's a best practice with GraphQL to avoid making backwards incompatible changes. But we're human. Sometimes we make mistakes. So let's say that we do. We accidentally remove this avatar URL field that we were depending on in our client code. So I'm going to remove that code in our server. And then I'm going to regenerate the GraphQL Elm client code. And if I do a git diff here, you can actually see the generated code no longer has an avatar URL. So if we were to run the code in its current form, it would be broken. So what we'd hope for is that it wouldn't compile. If it doesn't work, it shouldn't compile. So let's check. If we compile our code, sure enough, it doesn't know what avatar URL is. So if you have a continuous integration server, you can run a quick check and make sure your client code still compiles before any GraphQL schema changes go live to guarantee that you don't have any breaking backwards incompatible changes. Okay. So cool. So we've kind of gotten this level of safety, not just in our server side and in our client side, but in the space between the two. So if it compiles, it works, and we're in our happy place again. Now, let's talk about interacting with JavaScript through ports and flags, JavaScript-interop. So again, when we're operating within Elm, we're happy. Things are nice and clean. If it compiles, it works. And then when we're operating within JavaScript, we don't really know what types things are. We don't really have those guarantees, right? So of course, we don't really know what can we send out to JavaScript, what can we get back from JavaScript, because JavaScript doesn't even have those guarantees. So how could it in the space between? So let's talk about TypeScript. So TypeScript is semantically the same as JavaScript. It's simply a superset of JavaScript. So it adds some features like being able to add type annotations and give you some pretty decent type checking. It's got really solid editor integration and auto-completion for a lot of different editors, and it's got some cool ways to describe different types, including union types. And it's really easy to get started. You just add a tsconfig.json. It also has this cool feature where you can just do npm install @type/your npm library, and for a lot of different libraries, it'll just download some type declarations that describe the API that you're using. So you get auto-completion and type safety for this npm library, which is pretty cool. A lot of npm libraries ship with this, including Electron.js and Moment. So a quick note, why use TypeScript and not a compiled to JS language like Reason and PureScript? These are really interesting projects, but when I'm doing JavaScript interop, I tend to do that because I want to use the web platform or something in JavaScript. And so I don't want another level of indirection to doing that. I just want to add a little bit of safety on top of JavaScript. So that's why I tend to prefer using TypeScript in my own projects. I kind of want to avoid that double interop. I don't want to reach out to ReasonML, and then ReasonML has native bindings to JavaScript from there. I just want to go straight to JavaScript with a little more safety. OK, so cool. So TypeScript gives us a little more safety and some more guarantees when we're operating in the JavaScript space. But our flags could be wired in completely incorrectly. We still don't really have any certainty there. It could compile and not work. So let's do a demo of another library I've built called elm-typescript-interop. So let me set up my screens here. All right, so I've got Moment.js installed here, and I want from my TypeScript file to pass through a localized time. Since I don't have that in Elm right now, I just want to use this library to do it. So to start, I'm going to pass in a string as my flag. Now I've got something running in the background that will rerun this command line tool, elm-typescript-interop, to generate these type declarations for my Elm code every time I change this Elm file. So actually you can see right now it says the type of the flags is null, and when I change the flags to a string here, it's auto-generated this, and now it knows that it's a string. So this is just a declaration file that tells it what the types are going to be for my Elm code that I import. So cool. So now I can pass in a flag. And notice my TypeScript file doesn't compile because I'm passing in null for the flags instead of a string. So let's pass in a string. And let's use that string in Elm. And cool, we're getting our localized time from TypeScript. Now, often I find that I want to refactor these types. So, let's say I'm expecting to pass in more data with my flags. So as a refactoring, I'd like to wrap this in a record. I'm going to call it start time. Now, Elm knows that something's broken here and I need to fix it. The question is, does TypeScript? And as a matter of fact, it does. And in fact, when I start typing start time, it gives me auto-completion. It says, you probably want to pass it through under this field. So cool. So that refactoring was super easy. And now that it compiles, I'm very confident that it works. Now, I've got a little stub subscription here. So I've already wired it in on the Elm side, but I'm going to need to make it into a real port instead of a stub, and then utilize that port from the TypeScript side. So every second, right now I'm just console logging the current time, but I want to send it to Elm now. So I'm going to do app.ports. And I always forget the syntax. Things don't really stick in my brain. So for me, just having the auto-completion is quite nice, because I always forget the syntax. So I can send a clock reading, and if I forget to add the parentheses, it knows, hey, you're sending this function, you really should be sending a string. Okay, so cool. It compiles, it works. Our clock is now running. And then one last step, let's send out in a port from Elm to TypeScript. We want to tell it to set it as a new locale. And again, I've already wired this in to send out these messages, but our current command, set locale, is just a little stub, command.none. So let's make that a real port, and let's listen for that event from TypeScript. So when set locale happens, we want to subscribe to that. We want to take the locale, and we want to call set locale with our new locale. Okay, so cool. Now we can change the localizations in TypeScript. Thank you. So we've kind of taken this uncertainty that we've got interacting between Elm and TypeScript, and we've got this feeling again that if it compiles, it works. So we're in our happy place. So a note about these types of libraries, often there are opportunities to eliminate these types of avoidable uncertainty in places where we have variable contracts. So for example, APIs, we eliminated some uncertainty there. Databases and storage also have variable contracts. So for example, local storage. So if you have message passing, again, this could be an opportunity for using some code generation and types without borders techniques to eliminate some of that avoidable uncertainty. So with message passing, for example, the Electron.js framework for building cross-platform desktop applications has basically a web application that it renders as your desktop application, and then it has a global process which will handle things like, I want to quit the application, I want to minimize it. So to communicate those messages, you need to do message passing. So you can send a message with associated data, resize the window to these dimensions. So that's another opportunity for creating that safety in the interop between. With custom elements, you have these custom events that occur. So again, that's another opportunity where we have this uncertainty. We get custom events coming in, but what types of events can occur? And what does the data that they send look like? So that's another opportunity we could explore. And in general, any user-defined contract could be an opportunity. So here's a crazy idea about local storage. Imagine if we had a schema for our local storage. So we could store some sort of transient settings in our local storage. So for example, here we've got our schema is a first name that's a string and a last name that's a string. So right now it's Jane Doe. And then we want to migrate that schema over to a new version. And it just has a full name instead of first name and last name. And so we migrate it over and we get a full name. So we could imagine generating something where instead of getting a result back when we try to grab something from local storage, which is just giving us back a string that we decode, it would instead give us typed data that's, that we can guarantee is going to be of the correct type. So Mario Rogic actually kind of explores this idea, and I believe he's continuing to explore it. I definitely recommend checking out his Elm Europe talk from this year, Evergreen Elm. And I've got links to this and all the other resources at bit.ly/typeswithoutborders. So I'm interested in sharing more with the community about some of these code generation techniques that I've explored. It might seem intimidating, but really code generation is more tedious than it is difficult. So I'm interested to share blog posts and talks. I'd love to talk to anybody who's interested in this subject. I've got some ideas and some techniques that I've discovered for end-to-end testing my code generation libraries that make it really easy to iterate on them and make me feel really confident about the code. And I've got some ideas for extracting out some libraries in order to make code generation easier for the community. So if you're code generating a library, you have to use a lot of the same techniques of building a library. So I recommend these resources. These really helped me in doing that. Again, bit.ly/typeswithoutborders has all these resources. Okay, so to summarize, whenever you see uncertainty in your application, be skeptical. Is this avoidable or is this unavoidable uncertainty? If you see a result or a maybe, be asking yourself that question. Let's try to eliminate this avoidable uncertainty so that we can be operating in a world where if it compiles, it works, rather than just modeling that uncertainty. And we saw that we could move some of those uncertainties into compiler errors, like with GraphQL and TypeScript-interop. There are some other spaces we could explore, moving things over to the left and getting compiler feedback. And I'm really interested to hear the community's ideas on this. #TypesWithoutBorders. Let me know your ideas, and that's all I've got. Thank you very much.